Hello everyone, this is Nur Imtiazul Haq from Department of Electrical and Computer Engineering from Florida International University. Today I am going to present our paper naming BIoTA Control-Aware Attack Analytics for Building Internet of Things that is recently been accepted in IEEE SECON 2021. This is the outline of my presentation. At first, I'm going to talk about the motivation of our work and will provide a short introduction. Then, a brief overview of the smart building HVAC control system will be provided. After that, I'll talk a bit about our proposed framework, followed by discussing the main contribution of our paper, which is formal attack analysis. A short case study will be discussed afterwards. Then I'll talk about the test beds that we are considering for our work. After that, evaluation results will be described, followed by concluding my presentation. Contemporary smart building control system adopts Internet of Things based demand control heating, ventilation and cooling to make the building smarter, reliable, cozier and energy efficient. The addition of these less secure Internet of Things based sensor nodes and open communication network increases vulnerability of the system. And exploiting those vulnerabilities, the attackers can manipulate the controller with false sensor measurement injection and thus can disrupt the system's consistency. A recent report shows that a cloud service provider that connects 55,000 HVAC systems is vulnerable. Another report from a cybersecurity firm, Forescout Technology, says that almost 8,000 Internet of Things based devices are vulnerable to various cyber attacks. In our work, we propose a novel building Internet of Things analyzer framework that can measure the smart building HVAC control system security using formal method. Our proposed framework's efficiency has been verified on two state-of-the-art datasets, naming the commercial occupancy dataset and KTS live in lab dataset. In this slide, I'm going to talk a bit about the smart building HVAC control system and its components. The air handling units is the core component of the smart building HVAC control, which is responsible for maintaining the indoor air quality of the smart building. Several factors are responsible to contribute the energy consumption of a HVAC control system, like the occupancy pattern, weather condition, etc. And occupants' comfort depends on the indoor air quality and the desired set point temperature. The HVAC control system attempts to utilize the recirculating zone air for the energy efficiency of HVAC control, which in turn raises the concentration of the carbon dioxide and other volatile organic components or the air pollutants. So the fresh and returned airs are optimally mixed to supply through the supply vents, and those and the polluted air are returned through the return vents. And the coils are the main source of cost in a HVAC control system. The proposed BIoTA framework feeds HVAC control constraints, the cost calculation constraints, and the attack constraints to a satisfiability modular theory-based solver. The HVAC control constraints are generated using the building properties like building floor plan, the properties of the zones, the sensor measurements, etc. The attack constraints are dependent on the attacker's capability, attack goal, attacker knowledge, and accessibility to sensor measurements. The cost calculation constraints basically determine the attacker's success. The problem can be viewed as a constraint satisfaction problem where the SMT solver solves the satisfiability of the constraints using a solver that outcomes set or unset results. The unset result signifies that there is no possible vulnerability based on the given constraints, where the set outcomes are attack vector. So if there is any attack path possible, the solver guarantees to find one which is termed as the attack vector. The formal attack analysis is the main contribution of the paper. The main challenge of the attack analytics is the constraints acquisition from the control system, the cost calculation system, and the attack model. The HVAC control ventilation dynamics is modeled using mass balance equation, where the temperature control is modeled using the energy balance equation. The equation 1 and 2 are used for presenting ventilation and the temperature control constraints. In this work, a verification model is also considered that verifies the consistency of the measurements. The equation 3 and the equation 4 are used for the validation constraints in the control system, which validates the measurement in inconsistency based on the last control periods. The cost calculation is basically dependent on the supply and the mixed air temperature. The cost calculation equations, the 6, 7, 8, and 9 are basically uses the psychometric values of based on the American Society of Heating, Refrigeration, and Air Conditioning standards. The overall cost of HVAC control is mainly dependent on the coil cost and the chiller cost. A stealthy attack is an attack in which attacker alters system states without notifying the system's abnormality detection system. The attacker's knowledge about the system determines the attack's stealthiness. In this work, we consider a knowledgeable attacker who is aware of the surrounding weather pattern, building attributes, occupancy information, underlying control and defense mechanism of a smart building HVAC control system. In the BIoTA framework, we consider two different attack goals for launching an attack. One is increasing energy consumption, another one is obstructing occupants' comfort. The energy consumption attack is a straightforward attack in which the attacker attempts to change the sensor measurements to maximize the overall energy consumption in the building by forcing the control system to flow more fresh air in the supply airflow. For compromising sensor measurements of a particular zone, attacker needs to alter the sensor measurements of other sensors of that zone by bypassing the controller's anomaly detector. The altered sensor measurements needs also to be comply with the controller verification. Along with the verification with these things, the controller also considers the inconsistencies of entrance occupants count with the sum of zone occupants as well. For successfully launching an attack, the attacker needs to compromise multiple sensor measurements. The altered occupancy sensor measurement of a zone must be less than the maximum capacity. The equation 10 and 11 are here representing the attacker's goal constraint, and the equation 12 and 13 are representing the attacker's capability constraints. As I discussed before, in this work we have used two state-of-the-art dataset, naming the commercial occupancy dataset, which is located in Pennsylvania, and another one is KTS Testbed, which is located in Sweden. The occupancy pattern of both the COD and KTS datasets are normally distributed. In figure 3, we can see the occupancy pattern of this testbed data. So in the COD dataset, there are basically 5 zones: the laboratory zones, the warehall zones, the Clemente zone, and 2 entrance zones. And for this work purpose, 2 entrance zone occupancy are combined. In the KTS dataset, on the other hand, there are 3 zones: the living room zone, the kitchen zone, and the bathroom zone. So in the COD dataset, the laboratory zone is the mostly inhabited area and while the KTS dataset, the living room is the mostly occupied zone. The COD dataset contains almost 1 year of data, while the KTS dataset or the testbed contains 1 week of data, and the missing information has been interpolated. So this table 1 shows the zone properties of all the COD and KTS testbed data. Although 4 case studies have been conducted for the work, in this presentation I am showing a simple case study that has been conducted in a 5-zone commercial building of a core region located in Pennsylvania, and the capacity of the building was 135 persons in 5 zones. The attack intent was to increase the overall energy consumption of the building. As the entrance of the building is considered in this work to be robust against attacks, the main attack idea was to mislead the controller by showing more people in the hard working zone. In the hard working zone, the carbon dioxide emission and the heat radiation of the person are higher than the less hard working zones. So the case study here is performed by adding 17 people in the occupancy measurement, which is determined by the satisfiability modular theory based model of more pollutant generating zone and balancing it with another zone by subtracting 17 people from that zone. Due to the compromised measurements, the controller supplies 56% more air than required in one zone, whether another zone gets 13 times less airflow. The result shows that continuous attack throughout the year can obtain almost 10% increase in energy cost. Here are some evaluation results. So the evaluation results from the commercial occupancy dataset, it can be seen that if the attacker has the accessibility to all the 5 zones, then there can be a possibility of $303.95 US. But if the attacker has only accessibility to these specific 2 zones, which are the Clementine and Warhol zones, the attacker can incur only $3.75 US of increase. The similar thing can be seen as in the KTS dataset as well. In a very small apartment, the energy consumption attack can incur up to $8.95 US of increase. So from figure 3, it can be seen that if the discomfort attack based on carbon dioxide concentration and the temperature of the commercial occupancy dataset can also perform some significant damage to the occupants. For example, here from this graph we can see that although the ASHRAE standard suggests that the 1000 ppm is the maximum tolerable limit of carbon dioxide concentration for the occupants, here due to attack the carbon dioxide concentration in several zones has risen up to 1900 ppm, which can cause severe damage to the occupant's health. The same thing can be seen for the temperature increase attack scenario as well, where you can see that almost 20% to 20 degrees Celsius of temperature increases can be seen. So in the scalability analysis of the both dataset, we can see that increasing the number of zone actually increases the complexity of the solvers. Especially for the unsatisfiability cases, the solver complexity grows exponentially, which means that the system is not completely scalable. The building IoT-based HVAC control system is gaining popularity because of its reliability, efficacy, and cost efficiency. However, due to increasing cyber attacks, attack analysis of building IoT system needs more attention. Our proposed attack analysis on the smart building HVAC control system using the BIoTA framework suggests that the exploitation of vulnerable sensor measurement of the building control system can result in a significant increase in cost and also raise several health concerns for the occupants. And it can also violate the comfort constraints of the occupants as well. A proposed attack model is verified using two state-of-the-art datasets, where the core dataset evaluation result shows that using energy consumption attack, the HVAC control system can encounter an additional cost of $300, which is 10% more than the usual. We plan to study the cyber attacks that exploits multiple sensor building control systems running independently to create a deeper cascading impact in later. We'll also try to gather the constraints from the contemporary smart building HVAC control system for our future work purpose. So thank you everyone for listening. So this is my email address to reach me out if you have any questions.